14.4 is about length of curve, same as arc length, something you have seen before back in calculus too. Actually, you look at least at three versions of finding arc length. The scalar version when you're given a function f of x, number two the parametric form, and number three the polar form. So in this case, we're going to take it from the parametric form because if you look at the integral we have for the arc length dx dt squared plus dy dt squared, that looks a lot like taking derivatives of a set of parametric equations. Where are they going to come from? Well, they're going to come from the components of a vector valued function. What are we going to do in this class? Well, add a third term for a curve in space. That's to find the arc length in space. Well, I'm not going to go through the whole derivation of the formula, but if you want to see it, on the playlist I have on Canvas for Calculus 2, look for this topic, and I have a detailed version of this derivation. So I'm just going to give you a brief idea of how we get the arc length. All right, so briefly, so arc length, it's an integral to calculate the displacement to go between point A and B along the curve, or along a line, or along, well, any curve C, right? Well, of course, the shortest distance is going to be like a linear distance, but that's not actually the accurate result, right? Because we would be missing all this part, all that part, etc. Okay, so so in a similar way, we found the area under the curve, Riemann sum, the first time you were introduced to integration. So you divided the area under the curve into rectangles, all right? 2 rectangles, 5 rectangles. The more rectangles, the better. In a similar way, in this case, this is not about area. This is not about rectangles, but I could do this distance plus that distance plus that distance, 3 distances. The distance, the total distance or the total length, it's getting better, but still it's not quite the actual distance. So how about this, that. So in this case, I subdivided this arc length into 1, 2, 3, 4, 5, 6 arc lengths. Well, it's giving us a better result, but it's not quite the actual result. Well, again, in a similar way as in Riemann sums, we chop the region into infinitely many rectangles. We will chop this length into infinitely many arc lengths. But in the end, I will just choose one representative length, say this one, all right? Where I have this, let me call this L sub I, okay? So this distance right here generates a right triangle, if we will. That is because to go from this point A to this point, say X sub I, Y sub I, if you will, right? It takes some displacement, delta X sub I, delta Y sub I. Let me call this delta L, right? Not just. Well, so how do we get that length? Let me get rid of the delta. I don't think we need the delta for this. Okay, how do we get the L? Well, isn't that just Pythagorean theorem? I mean, so L sub I squared equals to delta X sub I squared plus delta Y sub I quantity squared. And if you take L sub I, that equals the square root of delta X sub I squared plus delta Y sub I squared. But that's just the length of the representative length I used to, in a way, get this model, right? Now, here's the thing. In the same way that we use Riemann sums to add infinitely many of those lengths, or infinitely many of those areas to get the area under the curve, we would add infinitely many of those. What did you get when you add infinitely many of those quantities? The integral, right? So this is where the arc length formula basically is coming from. But again, do you want to see the details of this? Just have a look at the playlist on Canvas. Look for the arc length. You'll see the algebraic maneuvers it takes to get this, all right? Okay, so now let's put vector notation to this. Well, again, in this case, what we have a curve defined by a vector valued function with components x of t, y of t, and z of t. So now we're extending this to curves in space on the interval a and b. All right. So this is going to be the integral of the derivative of the x component squared plus the derivative of the y component squared, which is what we saw back in Calc 2. You know, it's essentially a different way to denote these quantities. But now we're adding the derivative of the z component squared now. Putting all these together, this big madness here, the square root of these sums of squares, isn't that just the magnitude of the velocity? Putting together vectors and all that, that's all it is. So the arc length, in a different way to define arc length, then it's the integral of the magnitude of the velocity, right? That's more compact, if you will. Okay, well, let's have a look at an example and see how this goes. All right, so find the arc length. Find the length of the curve r of t square root of 2 times t. Careful, because the t is not inside the radical. E to the t and e to the negative t. Okay, oh, I forgot the limits of integration for t between 0 and 1. Actually, you will be given these limits all the time, right? So it's not like you, well, in some cases you may need to figure out the limits. That is when you're not given the limits with respect to, but you're given order pairs or order triples. But you know how to find the values of t for a given point. We did that last time, or yeah, I don't know. I mean, yeah, that was yesterday. Yeah, today's Tuesday. So, okay, so let's find the velocity, or r prime. Yeah, r. It's a velocity. Okay, with the velocity, which is v of t. Oh, just the velocity first, not the magnitude. That is the derivative of root of 2 times t. That's just root of 2. Comma, the derivative of e to the t is itself, and the derivative of e to the negative t is also itself, times the derivative of the exponent, which is negative 1. That's just represented by a negative in front of the exponential. What do we need? So let's find arc length. That is the integral from 0 to 1 of the square root of 2 squared plus e to the t squared plus negative e to the t quantity squared dt. Okay? That equals then, well, the radical here cancels the 2. I mean, the radical cancels the square, not the 2, the square. And that's going to leave us with the integral from 0 to 1 of 2 plus e to the 2t plus, careful, negative being squared becomes positive, and power of another power, multiply the powers. E to the negative 2t. Oops. dt. All right. Here's where the fun begins. How do we integrate this function? U substitution. Okay, well, should we set the quantity inside of the radical equals to u? Well, yes, you can do it. You may do it. Take the derivative, but you don't have anything outside to represent the du part of the problem in this case, right? So, any other ideas? Separate them, like take the square root of every single term. Careful with that, because when you have the square root of a plus b, this is not the square root of a plus the square root of b. Put some numbers. The square root of 25 plus 9, for instance. Is that equal to the square root of 25 plus the square root of 9? Well, this is 5 plus 3, which is 9. 25 plus 9, oh, that's 34. Is 9 equal to the square root of 34? So careful. This is a very common algebra problem. I get to see this even on exams on a question like this. So careful. You can't distribute the radical over a sum of difference of terms, or raise a power over a sum of difference of terms. So any other ideas how to? What is that? Raised to the 1/2. How is the raised to the 1/2 could help? but I still need a du outside here, right? To stand the u du part of the problem. So we can perform this substitution.
Multiply it by its own, like a radical, so plus 2 to the 2x plus.
The thing is, if I multiply by itself, I would be changing the value of the expression. So it's like multiplying by 2, for instance. It's no longer the same value. All right? Okay, so this means here we need to do a bunch of algebra. Here we need to factor perfect square trinomials. But hold on, where is the trinomial? I see exponentials, no x's to the power 2. Well, so here's the thing. Number one, I'm going to write this in a slightly different way. That means I'm going to write it from 0 to 1, okay, the integral from 0 to 1, and I'm going to write e to the 2t plus 2. I'm going to leave a space for something you'll see, plus e to the negative 2t, okay, dt. So somehow we're going to turn that expression inside of the radical into a perfect square trinomial, write it as a binomial square to cancel that square with the radical. But how are we going to turn this into a perfect square trinomial? Number one, what's a perfect square trinomial? That is, okay, we want to see the pattern a squared plus 2ab, or minus, in this case it's a plus b squared, and that equals a plus b quantity squared, right? So somehow we want to come up with this, and actually maybe it's not obvious, I agree, but it's there already. Let's summon some of the factors to make it look like it. Well, so do you guys agree that if I multiply this by 1, I am not changing the value of the expression? Multiplying by 1 doesn't change anything, but you can express that number 1 in your favorite way. 5 over 5 over 5, 7 over 7, a million over a million. How about, e to the t divided by e to the t? Isn't that equal to 1 as well? Okay, let me move the denominator to the numerator with positive exponent. That means the integral from 0 to 1 of the square root of e to the 2t plus 2 e to the t e to the negative t plus e to the negative 2t. Now, does that look like a squared plus 2ab plus b squared? Isn't that a perfect square trinomial? Right? Okay, so that means we can express this dt as the integral from 0 to 1 of the square root of e to the t plus e to the negative t, quantity squared, dt. And here is where we can cancel the radical with the power 2. And we would be integrating from 0 to 1 e to the t plus e to the negative t dt. All right? That is e to the t itself minus e to the negative t from 0 to 1, e to the 1 minus e to the negative 1, that's the upper limit minus lower limit, e to the 0 minus e to the negative 0. That is simply e minus e to the negative 1, and then e to the 0, which is 1, minus e to the 0, which is simply 1. That's simply, it's just this. Maybe e minus 1 over e. Any of these two are acceptable, right? So, okay, so here is the thing. If you're not very happy with what we did right here, with the multiplication by a 1 and then turning it into a perfect square trinomial, let me show you another alternative. So you guys want to use the back side of the page? Let me show you a different way. And well, I'm going to skip the radical symbol. I'm just going to go with e to the 2t plus 2 plus e to the negative 2t. Okay. Now, let's see. So, again, my goal here is to come up with a couple of perfect square trinomials. But instead of doing that weird trick, if you're used to that trick, that's fine. You like that trick, that's fine. But in this case, I'm going to go with e to the 2t. I'm going to leave a space for, you'll see, plus 2 plus 1 over e to the 2t. Now, think of the first two quantities as quantity over 1, and guess what? We will this time combine fractions together by finding the least common denominator. That is, I would need to multiply by e to the 2t and divide by e to the 2t, e to the 2t, e to the 2t. Right? Like combining fractions with different denominator. Well, now that we have the same denominator, that is e to the 4t plus 2e to the 2t plus 1, everything divided by e to the 2t. Okay? And well, let's have a look at the numerator. Doesn't that numerator look a lot like a quadratic pattern? So, like this. That is e to the 2t squared plus 2e to the 2t plus 1 over e to the 2t. So in this case, again, we have maybe an easier to visualize version of the quadratic form of the perfect square trinomial. That is a squared plus 2ab plus b squared. Right? So this could be e to the 2t plus 1 squared over e to the 2t. All right? Now, how is that going to simplify better than what we did before? Well, let me go back to the integral. Right? This is back to the integral. Well, so we may cancel the square with the radical, but also this 2t divided by the invisible 2 there cancels out, leaving us with the integral of e to the 2t plus 1 divided by e to the t. Okay? And using laws of exponents, e to the 2t divided by e to the t, that leaves us with the integral of e to the t, and 1 over e to the t, that's simply e to the negative t. Isn't that the same integral we got at the end? Right? So now, it's up to you. How you want to do? Do you want to do the weird pattern, or do you want to combine fractions together and then see the quadratic pattern? Either way, somehow on a future take-home quiz, I'll give you something similar like this, so you can choose your favorite method, okay? Alright, so that was our first example of finding arc length. It's very formulaic. There's nothing too crazy about it. The crazy thing about could be, all these algebraic techniques about how to simplify the integrand.